de la reunión anual número 35 de la División de Partículas y Campos de la Sociedad Mexicana de Física. Y hoy tenemos una serie de pláticas de teoría cuántica de campos, pero creo que sobre todo de partículas elementales que a todos nos gustan mucho, por supuesto. Entonces, nuestro primer orador es Alan Hernández Juárez, quien nos va a platicar acerca de este interesante tema, como ustedes pueden ver. Sin quitarle más tiempo, él desde la UAP nos presenta este trabajo. Adelante, Alan.
Hello to everyone. Thank you so much for the opportunity. And today I'm going to talk about contributions to CCB couplings from CP violating flavor changing couplings. This work is in collaboration with Dr. Agustín Moyot and Dr. Gilberto Tavares Velasco. And well, okay. So first I'm going to talk about the theoretical framework. We are interested in trilinear neutral gauge bosons couplings with two on-shell C bosons and an off-shell B boson. This coupling can be parameterized by two form factors, F5 and F4. F5 corresponds to the conserving form factor, and on the other hand, F4 is the CP violating form factor. For describe this vertex, we are using the kinematics depicted in the figure. And well, we can note from equation 1 that here in this term, that when the B boson becomes on-shell, then the vertex cannot exist. Thus, to induce a trilinear neutral gauge boson coupling, we need at least one boson off-shell. And we are also interested in trilinear neutral gauge bosons couplings with new gauge bosons, for example, maybe a C prime boson. These bosons are predicted in models of new physics or beyond the standard model. And again, the coupling of two on-shell C bosons and an off-shell C prime boson can be described by the same two form factors. And well, and here it's important to say that we are only considering contributions from dimension 6 operators. And here it's important to say that we note in equation 2 that in this case, when the C prime boson becomes on-shell, the vertex can still exist, and this is very interesting. So, as I said, we are interested in CP violation. So we will need flavor changing neutral current couplings mediated by the C gauge boson, and these couplings can be expressed by the equation 3, and here we observe the non-diagonal couplings of the C boson. These couplings, we assume they are complex. This is because we are interested in the CP violating case, and because of the hermicity of the Lagrangian, these couplings must fulfill this condition. Okay, so the equation 3 can also be written in terms of the chiral couplings. This could be interesting, or very important for a numerical analysis. And the relation between the chiral couplings and the vector and axial couplings are described in equation 4. So we will use flavor changing neutral couplings of the C prime boson, and these couplings can be described by the equation 5. And these kind of couplings can exist in several models beyond the standard model, and here I show some examples of these models. Okay, so now I'm going to talk about the analytical results. And so first, I'm going to talk about the case of an off-shell photon. And in this case, we have to calculate 4 Feynman diagrams, but this diagrams follow from the generic diagram that I showed here in the figure. So we need to consider the exchange between the masses in the loop and the permutation between the two on-shell C bosons. Then we will obtain the 4 Feynman diagrams. Okay, in this case, it's not possible to induce the CP violation, and this has been verified in our calculation. But we can obtain the contribution to the CP conserving form factor, and it is expressed in equation 6. And here we observe this function, R. Okay, sorry. Here we observe a function at the end of the equation. And this function is in terms, it's a little complicated, but it is in terms of the Passari-Nobelman scalar functions. So next, I'm going to talk about the case of a off-shell C boson. And okay, in this case, we need to calculate 36 Feynman diagrams. But again, these diagrams follow from the 3 generic diagrams that I show here. So again, we must consider the exchange between the masses in the loop in the 3 generic diagrams. And in this case, we must consider the permutation between the 3 C bosons. Then we will obtain the 36 Feynman diagrams that we need to calculate. So in this case, we also obtain a contribution to the CP conserving form factor F5, and it can be expressed as in equation 7. And again, we observe a lot of functions which are in terms of the Passari-Nobelman scalar functions. And here we obtain something different because we can induce a CP violating form factor, and it is expressed in equation 8. So again, the S function, which appear at the end of the equation, it is in terms of the Passari-Nobelman scalar functions. And here we need to observe very interesting things. This part, the imaginary part of this combination of the axial and vector couplings. So then we observe that to obtain a non-vanishing CP violating form factor, we require that the flavor changing neutral couplings mediated by the C bosons, we need that they must be complex. And okay, so we can also observe that we need 2 different phases between the vector and axial couplings to obtain a CP violating form factor different of 0. And okay, and here we can observe this term. They are the masses in the loop. And okay, so as we observe here that we expect that the main contribution to the CP violation come from flavor changing neutral current couplings with the top quarter. So they will be the most interesting results for us. And it is important to say that this result has been never reported before, so this is the first time that it is presented. And now I'm going to talk about the case of a C prime and off-shell C prime boson. And Here, first, we need to consider the diagonal case where there is no flavor violation. In this case, the masses in the loop are the same. And for this calculation, we only need to consider two Feynman diagrams. So we only consider the permutation between the two C bosons, and we will obtain the two Feynman diagrams that we need. And here we only obtain a contribution to the CP conserving form factor, and it is expressed in equation 9. And as I said, there is no CP violating contribution in this case. So this result has been never presented before, and this is also very interesting. But the more interesting case is the non-diagonal case, where we have different masses in the loop. In this case, we need to consider 12 Feynman diagrams. And these diagrams, again, follow from the three generic diagrams that I show here. So again, we must consider the exchange between the masses in the loop and the permutation between the on-shell C bosons. And we will obtain the total contributing Feynman diagrams. And here again, we obtain a contribution to the CP conserving form factor, and it is expressed here, but here we obtain the contribution to the CP violating form factor. Again, the T functions are in terms of the Passarini-Nobelman scalar function. And it's important to say that here we observe that the CP conserving form factor is in terms of only real combinations of the vector and axial couplings, and the CP violating form factor is in terms only on imaginary combinations of the vector and axial couplings. And okay, we observe here this term. So we know that it is not necessary that the couplings, we don't need complex couplings of the C prime boson. We only need complex couplings of the C boson of the standard model to induce CP violation in this vertex, or in this case. So we have performed a numerical analysis. I show here some values that we use it for the couplings, and we find that in general the form factors are complex, and in the case of an off-shell photon, we find that both parts, the real and imaginary, are of order 10 to minus 3. For the case of a C and off-shell C boson, we find that for the CP conserving form factor, they are of order 10 to minus 6, and in the CP violating case, they are of order 10 to minus 5. But we must consider the value of the factor that we have here. And the results have been studied in the past, especially in the standard model case. And but they studied they studied the diagonal case, where they obtain results of order 10 to minus 2. For the C prime boson, we find similar results for the real and imaginary parts. So, but the most interesting are the non-diagonal, where we find that the the CP conserving form factor is of order 10 to minus 4, but the CP violating form factor is of order 10 to minus 7 or 10 to minus 8. And for both parts, the real and the imaginary. And for more details, you can see our last article, which I show here. And as conclusions, new contributions to trinidad network gauge boson couplings with an off-shell photon or an off-shell C boson are possible. Results for an off-shell C prime boson have been studied, and new sources of CP violation are possible in the case of the trinidad neutral gauge boson couplet with two on-shell C bosons and an off-shell C boson or off-shell C prime boson. Thank you so much for your time.
Thank you very much for this very interesting talk, Alan. I don't know whether there are any questions in the audience. Maybe they are shy and I should start. Well, I have a question indeed. I don't know whether your analysis is actually dependent on the gauge coupling magnitude, in particular of the gauge coupling of the Z prime with the rest of the matter, whether it matters what the size of this gauge coupling is.
Yeah, actually that's very important.
Yeah, it's there, right? Yeah.
We have studied a lot of models, but they have similar results. So the couplings could be a little different, but we obtain similar results. But yes, it is the coupling is very important. But in the case of these 5 models, we find similar results for all calculations.
Okay, very good. I don't know whether there are any further questions. So it seems not to be the case. Well, if not, then maybe we will we can pose the questions later. They will appear in the chat box. If you want to pose a question for this talk, for example, later, please be free to do so in the chat. Well, thank you very much, Alan, for this interesting talk. And then we have to move to the next talk. Thank you very much again.
Thank you so much.
And now we have here our next speaker. I invite Stefan Nellen. Stefan Nellen Mondragon, somewhere here.
Here I am. Hi.
Very good. Can you share your slides, please?
Sure. You can see it now, right?
Now, yes. And can you maximize just to, yeah, presentation form. Very good. As said, we have Stefan Nellen here from UNAM, and he's going to talk about some work that he did in collaboration with his fellows there. Please, go on.
Right. Yes. Well, good afternoon, everyone. Today we'll talk to you very briefly about the flavorful axiom and its relation to the Peccei-Quinn symmetry. This was done in collaboration with Leon Garcia, Newton Nath, and Eduardo Pinado, and you can find the full manuscript in the archive if you're so inclined. So the outline of this talk is that I will first be very briefly talking about axioms and flavor symmetries. And then parting from this, I will discuss a flavorful axiom model. Then some numerical results with this model, which help us constrain some free parameters and tell us a bit about its phenomenology, to then conclude. So, well, the Peccei-Quinn symmetry is an axial symmetry. It's a U1 symmetry. Was proposed by Ricardo Peccei and Helen Quinn in 1977 to solve the strong CP problem, which is a problem in QCD and in general in the standard model, where there is an extra CP violating term in the QCD Lagrangian coming from the topology of the gauge group. And it's constrained by it and a contribution coming from the quark mass matrices are constrained by neutron electric dipole measurements to be very, very small when considering how big in comparison CP violation is in the weak sector. It can be considered unnaturally small and thus problem. So the Peccei and Quinn solution was to introduce a scalar field and the associated symmetry to the standard model. And as this symmetry breaks, the axion appears as a pseudo-Goldstone boson, and this, which possesses also a quasi-shift symmetry and solves the strong CP problem by eliminating the problematic term. The axion as a particle itself was studied very, very shortly after the Peccei and Quinn's paper in 1978 by Weinberg and Wilczek independently. And well, we can treat the Peccei-Quinn symmetry as a flavor symmetry. In this case, we simply identified it with this Frogat-Nielsen symmetry. And what we get here is a flavorful axiom, or which also translates nicely to Spanish as acción sabroso. And why do we choose the Frogat-Nielsen symmetries when there are other flavor symmetries? It's because it provides us with a very simple and straightforward extension of the standard model, which can very easily explain the mass hierarchies for the fermions. And the way it's done is that you just couple the powers of the flavon to the standard model Yukawas. And when the symmetry breaks, you get powers of a parameter epsilon, which explain, if epsilon is small enough, of course, which explain the hierarchies in the different terms of the mass matrix. So with this in mind, we proceed to build a model based on the Frogat-Nielsen symmetry, which is also a Pichet-Quinn symmetry. We begin by the quark sector. You can see in this table the quark assignment, and we introduce a flavon, which we will call sigma. And since this is a KSVC style axiom model, we also have two Higgs doublets, HU and HT, though it is worth noting that these two Higgs doublets couple both to the up and down sector. So even though we have labeled them U and D, they are not exclusive to these sectors. And at leading order, we get two important results. The terms in the mass matrix are generated at dimension 5, with only the 3-3 generated at dimension 4. And further contributions are heavily suppressed since the next possible term comes from at dimension 8. So this is a good matrix with which we can work later on. Then we provide a UV completion of the quark sector. This is not only important because we want a renormalizable theory, but also because depending on the UV completion, we can limit terms which might be possible in the effective theory and prohibit some contributions to the mass matrix, and it also helps further guide us in our model. The first and the focus of this work is a type 1. It's an analogy to type 1 CISO for neutrinos. Here we introduce two heavy vector-like fermions, which and you can see here the diagram, the dimension 5 diagram, UV complete to this fermion. And the other is also an analogy to type 2 CISO for neutrinos, where we introduce heavy SU2 doublet scalars, and the corresponding diagram you can see on the right. Then, moving on to the vector sector, we need here a second flavon, sigma prime. This also distinguishes our model from the standard KSVC model, which only has one scalar singlet. This one has two. And who also possesses a hierarchy in its VEF being much smaller than that of the sigma prime being smaller. And its Pichet-Quinn charge is naturally also different. You can here see again the charge assignment for the leptons. And what's important in the lepton sector is that we get an A2 type structure from the type 1 CISO mechanism. Here we can see this N1 are kind of like stereo neutrinos, and giving us the following mass matrix from the neutrinos. And the A2 structure has also implications that we would have neutrinoless double beta decay at tree level and predicts a normal ordering for the quark mass matrices. And it's also worth noting that the mass matrix for the charged leptons is diagonal. Then the scalar sector can get quite complicated, especially if we take the type 2 CISO UV completion, since the scalar potential is quite big. In fact, in the type 2 CISO UV completion, we have about 40 terms. And nevertheless, since there is a strong hierarchy present in the VEFs, we can do some leading order predictions for these models. Anyway, the most important part in the scalar sector is naturally, for the judging from the title of the talk, is the axiom. And the axiom we can extract from the Pichet-Quinn Goldstone boson, since it must be orthogonal to the set Goldstone boson. So we just take away this contribution from the set Goldstone and get a physical axiom. And there are some important parameters of the axiom. The axiom decay constant Fa, which I forgot to mention before, is a free parameter of axioms, and it's a very important parameter. And it is inversely proportional to the mass and to the axiom photon coupling. We can see also that the axiom photon coupling is dependent on the quotient of the electromagnetic and color anomaly factors, which make it also quite heavily model dependent. Now, a nice aspect of the flavored axiom in particular is that there's a strong hierarchy. Since there's a strong hierarchy of the scalar VEF, we find that the decay constant is directly proportional to the vacuum excitation value of the sigma flavor. And in particular, we also find that n equals 5 and e equals 23/3. So using the SU5 grand unified theory as a benchmark, we find here that our axiom is suppressed by a bit more than an order of magnitude compared to that. So it couples weakly to photons. Then we conducted chi-square fit, which for completeness, I just added the tables here, but they are what's most important here is that we see also the hierarchies are present in the mass matrices, and our model can reproduce quite well actual data. The same for the lepton sector. We also see that the fit predicts also normal ordering in the neutrino mass squared mass differences, which is also a prediction of the A2 structure we obtained. And we can then use this chi-squared fit and the data it gave us to conduct further investigations. In particular, the fact that there are flavor violating Yukawa couplings can lead to quark decays with an axiom as a final state, which are quite interesting and can be used to constrain our model. And there's also readily available data from Mason decays. The most sensitive process for this, in this case, is the k-on to pi-on axiom decay from ineffective Lagrangian and the chi-square, the numbers on the chi-square fit, which can devise the following relationship in terms of the V sigma. And data from the E949 collaboration also constrain heavily. Oh, there's a one too much here, sorry for that. Constrain the branching ratio using the proportionality relationship from the axiom decay constant and V sigma. We can turn this branching ratio, this bound on the branching ratio, to a bound on Fa, which should be greater than 7 times 10 to 9 GeV, and in turn constrain the mass to be sub milli-electron volts and GA gamma to be also very, very small. We also did an analysis from B Mason to K on axiom decay, but the bounds coming from here are quite smaller than the K on decay bounds. I have included a plot which you can see current experiments and axiom bounds are solid and future projections are transparent. The two standard axiom models, the KSVC and the SFC model, are shown here, and our flavorful axiom model is about an order of magnitude weaker in GA gamma. And I also added here the K on decay bound, which our model should be below this. And we see also importantly that at least in the current future, the flavorful axiom will not be directly tested by these experiments. Then there's also the possibility of flavor violating decays mediated by the two Higgs bosons with Higgs doublets which are present. Another consequence of the VEV mass hierarchy is that the flavon VEVs are quite bigger. This is also important for the axiom itself, otherwise its mass would be too large. And we can decouple the resulting Higgs bosons after electroweak symmetry breaking from those resulting, or the remaining bosons from the Peccei-Quinn symmetry breaking. So we have a light which we identified to the standard model Higgs boson, which was detected by the LHC, which is small h, and a massive or more massive Higgs boson, which is big H. And these are in terms of an angle alpha and the Higgs bosons coming from HU and HT. Furthermore, we have two other, another free parameter, which is the standard model vacuum expectation value, and its relationship between VU and VD is given by the parameter beta. The flavor conservation limit in this case is given when tan alpha is equal to cotangent beta. For this, we study the top two Higgs charm decay, which is the most sensitive given our model, and derive a constraint from an effective Lagrangian and a chi-square fit, which can be nicely summarized in this picture. We see that Atlas has already proved much of the parameter space, which in the future, the LHC and clique experience will probe furthermore, leaving only the thin white band surrounding the flavor conserving limit. Then there's also quickly the possibility that the flavorful axiom is a dark matter candidate. We find that the relic density produced through the misalignment mechanism can be matched for 5 times 10 to the 10 GeVs to 10 to the 15 GeVs completely. So given the complete relic density. Since this model also predicts n equals 5, there's the possibility of the formation of domain walls. And this could pose a problem since they are not completely compatible with standard cosmology and would have to be either destabilized or inflated away in different cosmological scenarios. So to conclude this talk, we have shown that identifying the Pacheco-Wien symmetry with the Frogat-Nielsen symmetry yields interesting results. On one hand, we get a very elegant solution to the strong CP problem. And on the other hand, we get an explanation for the mass hierarchies in the fermion sector. And we also get VEV hierarchies, which are important for the phenomenology of this model. At leading order, we find quark matrices with NNI structures and a neutrino matrix with an A2 type structure, which also predicts normal ordering and neutrinoless double beta decay at tree level. These predictions are also compared to a chi-squared fit, which explains them or matches them, so to say. Then we can find from this model also a flavorful axiom. Its mass should be sub-milli-electron volt. This was done by bounding the axiom decay constant from K on decays, and also we find that the axiom photon coupling should be very weak. There's also flavor change recurrence, and it could be dark matter. And well, in the future, this kind of models can be explained with KSB set-like and promoting FN of PQ to a H symmetry.
Thank you very much, Stefan. Questions from the audience? I know these talks are very fast. Well, I do have a question. You said you made a chi-square fitting, yes. And I would like to know how you did that.
Okay. Yes.
These are all the weak parameters, right?
Yes, the quarks and leptons.
Yeah.
We adapted an algorithm from machine learning to optimize parameter space fits. So we minimize the chi-squared fit with an algorithm which is normally used in machine learning, which is deterministic, by the way. So no scan.
Thank you very much. Well, some other question? I don't see any question. Thank you very much for this very nice and interesting talk, Stefan, Nelen Mondragon, and I guess we have to move on. Thank you.
Thank you.
We invite Victor Munoz now.
Yes, can you hear me?
Yes, can you share your slides?
Yes. Do you see them now?
Yes, can you maximize them? Yeah, very good. So without further ado, welcome Victor Munoz from UNAM. Please tell us about your work.
Hello, everyone. The title of this talk is The Structure of Cosmic String of a U1 gauge field for the conservation of baryon number minus lepton number. Here we will discuss an extension of the standard model and cosmic strings, which are topological defects, as a possible consequence of this extension. Let me start by telling you what we know about baryons and leptons in the standard model. Baryon number conservation was proposed by Stockelberg in 1938 to account for proton stability. Lepton number conservation was proposed by Konopinski and Mahmoud in 1953 to discriminate if whether certain reactions were possible. But now we know that at very high energy, the standard model allows B and L conservation violation, even though this hasn't been observed experimentally. However, the difference B minus L is still conserved. It is an exact symmetry. As an exact symmetry, it is more natural if it were a local symmetry instead of a global one, as the traditional standard model treats it. So our proposal starts here, and it consists in gauging the B minus L symmetry group. But gauging leads to a B minus L anomaly. And this can be cured, fortunately, by adding a right-handed neutrino for each fermion generation. Furthermore, we can get a mass term for the right-handed neutrino via the Higgs mechanism, adding an additional complex scalar Higgs field chi. Now, let me remind you the Higgs mechanism in the standard model. The Lagrangian contains a Higgs field phi, which is a complex scalar doublet, and gauge fields W and B for SU2L and U1Y local symmetry groups. The Lagrangian reads like this. It has a kinetic term for the Higgs field with covariant derivatives D, a potential and gauge term. The potential is the Mexican hat potential, and the covariant derivative couples the W and B fields with the standard Higgs field. There is a case of symmetry breaking for m squared negative, and we can select this vacuum solution. If we add a real perturbation to this ground state, then we will find massive Higgs, W, and Z bosons. We will also find a massless photon, and leptons and quarks will acquire mass via Yukawa interactions, which are not written in this Lagrangian. As I mentioned before, B and L violations are possible at high energy in the traditional standard model. This violation appears through the Adler-Bell-Jaquif anomaly in the divergence of the baryon current. At the classical level, this divergence must be zero to get a conservation law, but upon quantization, this divergence gets a term where Ng is the number of fermion generations and all the other part is known as the Chern-Pontryagin density. The classical divergence gets quantum corrections known as sphaleron processes that allow the violation. The electroweak vacua is divided in topological sector. A sphaleron is an unstable solution of the equation of motion of the electroweak theory. It has sufficient energy to transition between topological sectors. Each transition can change the baryon number a difference delta B, which equals delta L. Hence, the difference B minus L is still conserved. And as I mentioned before, B minus L is an exact symmetry, and it is more natural if we gauge it. This is our proposal for an extension of the standard model. But gauging is not so simple. We call A mu the gauge field for the U1 symmetry group, and it turns out that gauging leads to an anomaly. The divergence of the B minus L current is non-zero. This anomaly comes from the fermion triangle diagram presented in this figure, where we have a triangle of fermions and the gauge field as the external legs. This anomaly can be cancelled successfully if we add a right-handed neutrino with B minus L equals to -1. Furthermore, we add an additional Higgs field to get a mass term for the right-handed neutrino, as we know that they should have mass. So our extension of the standard model consists in an SU2L and U1 local symmetry groups, where we take a linear combination of the hypercharge and B minus L in the U1 symmetry group. The Lagrangian contains the kinetic terms for the traditional Higgs field, the new Higgs field, a potential, and the gauge term. The potential is just the Mexican hat potential for both of the Higgs field, plus a coupling between the two Higgs fields. The covariant derivative couples the W and A gauge fields to the traditional standard Higgs field, but the covariant derivative of the new Higgs field just couples it with the gauge field A. And also we have this field strength tensor. Now, in the case of a first generation of leptons and quarks, we will have electrons, neutrinos, up and down quarks. The Lagrangian reads like this. It contains the kinetic terms for the left-handed fermions as SU2 doublets. We have a kinetic term for the right-handed fermions, and we have the Yukawa interaction terms, which give mass to the fermions via the Higgs mechanism. These terms are the same as in the traditional standard model. The new terms are the ones in the third line. We have a Dirac mass term to give mass to the left-handed neutrino using the Higgs field and the right-handed neutrino. And we have a Majorana-Yukawa-like term, which gives mass to the right-handed neutrino, and we use the new Higgs field. The neutrinos in the Majorana term give a charge B minus L equal to 2, thus the new Higgs field must have B minus L equals to -2. Now, let us start talking about topological defects. Before that, I'm gonna give you two important mathematical definitions. Let us consider two maps that preserve the base point, F and G, that goes from the n-sphere to a topological space or manifold. These maps are homotopic if they can be deformed smoothly into one another. They form an equivalent class, and each map is an element of a group called the end homotopy group. So here we have two topological spaces, and we control two curves alpha and beta. We can see that we can shrink alpha and beta to this point, so we say that these two curves are homotopic. But in the case of the Y topological space, there is a hole inside alpha prime. So beta prime can be shrunk to a point, but alpha prime cannot because of that hole. So we say they are not homotopic. Another important definition is the winding number of a curve, which is the number of times a curve turns over a point. Now, topological defects can be found within a great variety of systems. Some examples are quantized magnetic flux lines in type 2 superconductors. We can see in the figure vortices in the local magnetic field of a thin film of Wavco superconductor. We can also have vortices in superfluid, and we can see in this figure the visualization of vortices with a filament structure in superfluid helium-4. There are also dislocation and some proposals in and beyond the standard model with cosmic strings. Let us explore a little bit more the example of type 2 superconductors. Using Ginzburg-Landau theory, we can write the free energy density F as a series expansion in the wave function around a critical temperature. It takes this form. In order to obtain the equation of motion, we take a variation with respect to the conjugated wave function, requiring it to be minimal. This figure shows the contour plots of the solution with square lattice symmetry. In the right figure, we can see the current around the vortex. These are vortices in 3 dimensions, but the figures shown here are in an intersection with a plane. We have assumed set independence, so these both vortices have a filament structure along the Z axis. These are the magnetic flux tubes. Now we can ask what is the relationship between vortices and topology. Well, in general, for a scalar field phi, which transforms under the representation of a compact Lie group G, we let M be the vacuum manifold and be a point on M. Then for any element of the group, the product GB is also on the manifold. It is important to define the isotropic group H to eliminate points that are the same under an element of the symmetry group. In this way, the points on M are in one-to-one correspondence with the cosets M equals to G modulus H. A solution given by this equation of the field might be regarded as defining a loop in M, a map from the circle to the manifold. Whether or not there is a vortex solution depends on the topological characterization of this loop. Here, in our proposal, we use the symmetry group U1, and we have a non-trivial first homotopy group given by the integers. Now we will take our extension of the standard model and compute the equation of motion of cosmic strings. This is the goal of our project. We take U1 with this linear combination as a local symmetry associated to a gauge field A mu. The Lagrangian reads like this is the same as before. We have the kinetic term for both Higgs fields, the potential, and the gauge term. The potential is the Mexican hat potential for both of the Higgs field and a coupling between both Higgs fields. The covariant derivatives just couples A mu with a coupling alpha to the standard or traditional Higgs field. And for the new Higgs field, the covariant derivative gives us a coupling with the gauge field A and the new Higgs field. And we have also the strange field tensor. It is important to notice here that we are taking a heavy W gauge field and fixed fermion background because we are in a low energy regime and of course for simplicity. We take an ansatz in cylindrical coordinates in order to solve the equation of motion. So the Higgs field contains a radial part and an angular phase which has a winding number n. The new Higgs field also have an angular part and a radial part and an angular phase with a winding number n prime, and the gauge field is in the phi direction. Phi, chi, and a are real functions. With these ansatz and applying the Euler-Lagrange equation for the Lagrangian shown before, we can get this equation of motions. And we use the boundary conditions for the fields to be 0 in the origin in order to have continuity. We want the fields to acquire their ground state when R goes to infinity. And we have this last consistency condition for the gauge field. So this equation of motion can be solved with numerical method, although it's a little complicated. In all the plots I will present you here, I will use these parameters, b equals to 1/2, b prime equals to 1, and lambda lambda prime equals to 1. It turns out that the variation of this parameter does not modify the general behavior of the solution. Also, we take h equal to 1 and h prime equal to n prime. Winding numbers establish the behavior of the solution, and we vary kappa between -1 and 1. This is an interesting solution with winding number n equals 0 and n prime equal 1. Because taking as 0 the winding number decouples the gauge field from the traditional Higgs field, even though we have an indirect coupling between the two Higgs fields because of kappa. That's why the profile of the traditional Higgs field still gets modified. We also should note that it is not 0 at the origin because the winding number is 0 and we don't have problems with continuity. In general, we have asymptotically stable solution.
2 minutes.
This is the case for winding number are the same. The profiles also have asymptotically stable solutions. And this is the case where both winding numbers are non-zero, but they are different. The traditional Higgs field takes one loop around the cosmic string, and the new Higgs field takes 2 loops around the cosmic string. A difference with the other plots we can notice is that near the origin, there are solutions of the traditional Higgs field which are bigger than the new Higgs field. We can explain this because the new Higgs field requires more energy in order to take 2 loops around the origin. So by last, let me give you the summary and conclusions. As B minus L is an exact symmetry of the standard model, we gauge it with A mu. To cancel the B minus L anomaly, we add a right-handed neutrino. We give mass to the right-handed neutrino by adding a complex scalar Higgs field, a new one. And now neutrino can have Dirac and Majorana mass terms. We study cosmic string solution and identify their profiles for A, phi, and chi. We find the behavior of cosmic string being dominated by the winding numbers, and as a possible consequence, particles might change their masses while crossing the cosmic string. And that's all. Thank you.
Thank you very much for this interesting talk. Victor, any questions for Victor?
Well, I have a, between question and comment. Concerning this to cancel the anomalies, there is another solution, Victor, which is adding 3 right-handed neutrinos with charges -4, -4.
The B minus L anomaly?
It seems that Eduardo disappeared. In the meantime, any other question? A very naive question. What is a cosmic string? I mean, this is in the basics of this very talk, but I'd like to know just your general answer, just to have an idea.
It is a one-dimensional topological defect in the fields.
So it's something that you would see in nature, I imagine, right?
Yes. In principle, it might have effects in particles because it is changing the ground state of the fields. So if a particle travels through a cosmic string, it can change their mass. Also, cosmic strings, there are examples, for example, in the traditional standard model with electromagnetic cosmic strings, which produce gravitational waves, and there are experiments looking for them in the CMB and establishing a bound in the tension of the cosmic string.
Okay, nice. Some other question? Well, I don't see Eduardo coming back, and I don't see any further question. I would like to remind everybody that at the end of these 4 talks, there will be separate breakout rooms so that you can join the speakers in the separate rooms and ask them directly whatever you have in mind. I mean, really, come to these sessions because all your questions can be answered by them. Thank you. Well, thank you very much for this very nice, interesting talk, and then we have to move on. So I invoke Edgar Lopez. Edgar, are you around?
Hello.
Yeah, hi. I can hear you, but I cannot see your slides. Can you share your slides? Nice. Now to the very beginning and then. Very good. Can you just, perfect. Very good. Now we have Edgar Lopez Contreras as well from UNAM, who's going to talk about this interesting talk. Thank you, Edgar.
Okay. I'm going to talk about the 3D04 model and the Qcd phase diagram in the chiral limit. The Qcd phase diagram is in the non-perturbative region of the theory. At low baryon densities, between the hadronic phase and the quark-gluon plasma, there is a crossover, and at vanishing chemical potential, the critical temperature is approximately 155 megaelectron volts. Also, there is an hypothetical critical endpoint followed by first-order phase transitions. Here we show an schematic representation of the Qcd phase diagram. The masses of the up and down quarks are much smaller than the intrinsic scale of Qcd. So we can approximate its masses as 0. This is the chiral limit. And in this approximation, the theory has an U2 left cross U2 right symmetry, which can be written as an SU2 left cross SU2 right symmetry. This is the chiral symmetry cross and U2 responsible for the baryon number conservation, cross and U2 from the axial symmetry. In this approximation, the Lagrangian decouples in a left and right projections of the quark fields, where D is the covariant derivative and G is the gluon strength tensor. In this limit, the chiral limit, the chiral symmetry breaks spontaneously down to a single SU2, and this generates 3 massless Nambu-Goldstone bosons, the pions. At low baryon density, the phase transition is of a second order, and if we include the masses, the pions acquire mass, and the second order phase transition is replaced by a crossover. We employ the O4 nonlinear sigma model, an effective theory of Qcd. Its action is given by this expression, where Fp is the pion decaying constant, and the fields live in the 3 sphere. We perform a pi-halves big rotation of time axis. This is known as the Euclidean time, and it is identified as the inverse temperature in natural units. We also perform a high temperature dimensional reduction, where beta is approximately 0, and the field configurations are approximately constant in the Euclidean time. So we can write the Euclidean action with a beta factor. This theory, the symmetry of this theory breaks spontaneously down to an O3, and this symmetry breaking is locally isomorphic to the chiral symmetry breaking. Also, these two symmetry breakings are conjectured to be in the same universality class. This theory has topological sectors in 3 dimensions, characterized by an integer topological charge. The topological charge identifies the third homotopy group classes, given by this expression. Geometrically, the topological charge is the winding number around the tree sphere. And the topological charge is conserved under infinitesimal transformations. It was shown that the topological charge represents the variant number. And this tells us that although our fields are mesonic, the topological excitations are baryonic. We can add a chemical potential with the topological charge. And as we have only mesonic fields, the resulting Euclidean action has no sign problem in contrast with Qcd. The lattice regularized Euclidean action is given by this expression, where the sum is over nearest neighbors, and Q is the topological charge, and we included two new variables, the inverse temperature and the baryon chemical potential in the lattice. And this expression is in lattice units. We can extract a physical meaning of these variables using the critical temperature at vanishing chemical potential from the literature, and we can translate the lattice units in physical units by means of these expressions. We used cubic lattices, and we assign periodic boundary conditions to our field. This ensures that the field covers all the tree sphere, and thus the topological charge is an integer. We measured several observables, among them the magnetization density, the energy density, the topological charge density, the magnetic susceptibility, the specific heat, and the topological susceptibility, given by these formulas. In our simulations, we used a multi-cluster algorithm, which performs collective spin updates. This has the advantage that diminishes the autocorrelation time of the observables, especially of the topological charge, that is a problem to change it with other algorithms. We explored the temperature region to find the critical temperatures, and we simulate near these critical temperatures. We used several baryon chemical potentials in lattice units from 0 to 2.5, and in physical units from 0 to 362.7 megaelectron volts. Our statistics is at least 10,000 field configurations, and we made our measurements such that the autocorrelation time is approximately 1/2. That ensures that our measurements are decorrelated. A previous attempt of this study was made by Miguel Ángel Nava Blanco. Here we show some results for our magnetization. The maximum slope of this observable is related with the critical temperature. And we can see in this plot that the critical temperature moves to smaller temperatures as the baryon chemical potential increases. Here we show the energy density in a lattice of volume 20 cubed in the same set of baryon chemical potentials. And we also observe that the slope of the energy density increases near as the baryon chemical potential increases. Here in this last plot, we see that this plot has almost a jump. This is an indication of a possible near first order phase transition. Here we show the topological charge density, that at a vanishing chemical potential, it should be 0 due to the parity symmetry. And we observe that also it the slope of this observable increases near the critical temperature as the baryon chemical potential increases. And in this last plot, it has also almost a jump that also indicates that a possible first order phase transition is near. Here we show the magnetic susceptibility that is a second derivative of the free energy. In the thermodynamic limit, it should diverge, but in a finite lattice, it has a maximum. This maximum is related with the critical temperature, and we can identify the critical temperature by means of this maximum. Here we show the magnetic susceptibility in a baryon chemical potential of 2.5 in lattice units and in several lattice volumes. We observe that the maximum of the magnetic susceptibility depends on the volume. This is the typical behavior of a second order phase transition. So we can ensure that in our studied region, we only found second order phase transitions. Here we show the specific heat that also is a second derivative of the free energy, and the maximum also is related with the critical temperature. Here we show the topological susceptibility that also in the critical temperature it should have a maximum, and we can identify the critical temperature by means of this maximum. We used the magnetic susceptibility, the specific heat, and the topological susceptibility to identify the critical temperature, and we extrapolated this critical temperature to an infinite volume to obtain our phase diagram. Here shown in physical units. As we can see, the phase diagram of this theory is monotonically decreasing, as it is expected for the phase diagram of Qcd. Also, in this region, we only found second order phase transitions, but in this last point is where we found a possible, where we found indications of a possible first order phase transition near this point. Here we show a reference table from the literature for the critical endpoint estimations. In our work, we found that the critical endpoint should be at smaller temperatures than 125 megaelectron volts and at a baryon chemical potential greater than 363 megaelectron volts. This is consistent with some of these reference critical endpoint estimations from the literature. As conclusion, studied the 3D04 nonlinear sigma model and effective theory of Qcd with two flavors in the Decay limit that allow us to study the phase diagram of Qcd at non-zero baryon chemical potential without a design problem. We can follow the critical line up to a baryon chemical potential of 363 megaelectron volts, where we find the critical temperature of 125 megaelectron volts. And the critical line is monotonically decreasing as expected for Qcd. And we found only second order phase transitions and indications of possible first order phase transitions at somewhat larger baryon chemical potentials that were found. An study with quark masses included can be seen in the poster presented in this conference by José Antonio García Hernández. Thank you.
Thank you very much for this interesting talk. So, questions from the audience? don't be shy. This is an interesting topic. Let me just ask a question. So basically, you said that there are, in the phase diagram, you said that there are 3 different kinds of transitions, a second, fast, and this other funky transition, what was its name? This
Crossover.
The crossover. Can you explain us more about the crossover?
Yes. When we are not in the chiral limit, when the quarks have masses, the phase diagram of Qcd at low baryon densities has a crossover that is characterized by a transition between phases that is not perfectly defined. Is instead of a line is a region. It's not as defined as a second order phase transition. It is a more soft transition. And,
yep.
And this is the reason by which in previous lattice Qcd studies, the critical temperature at vanishing chemical potential where the measurements of the critical temperature were different for several teams.
Okay, but then in your work, you only confirm kind of the part of the red line, right? On the right, close to 0 mass. Is it right?
No, in this region, but in the chiral limit, it is replaced by a second order phase transition instead of a crossover.
Okay, thank you very much. So, further questions? Well, it seems that it is not the case. Then, thank you very much, Edgar, for this interesting talk, and thank you to all the speakers of this afternoon for giving these interesting talks, and in the very short time that you had, just really fulfilling all the expectations that we had. So now we have the breakout rooms. They are already open. Oh, someone changed the names. Oh, well, I don't know why. It seems that well, now there are some breakout rooms. Please just join the rooms with your name. I'm talking fast to the speakers, and then to the audience. Please go to these different breakout rooms in order to ask all the questions you can probably have on these interesting topics. Thank you very much to all of you. See you next time.
Thank you, Saul. Thank you very much. Yeah, so we're going to be in the coffee break now, and then we will continue with the poster session at 4, which starts at 4. Okay. And that is also going to be just another set of breakout rooms with the presenters.
José, Iván.
Iván, ya.
Vamos a tener un room por speaker de póster, o va a ser como algunos rooms, varios compartidos. ¿Cómo va a quedar el asunto?
Sí, la sesión de póster va a ser igual que ahorita, que son breakout rooms en el coffee break. Pero va a haber un cuarto para cada presentador de póster.
Para cada uno de ellos. Entonces van a ser 16 rooms. Si llevo contado bien los 17. Me pareció no.
disculpe, una pregunta.
Sí.
¿Cómo entro, disculpe, a los grupos de los break rooms? ¿Dónde tengo que...?
En la parte de abajo, bueno, en mi aplicación de Zoom hay una parte de abajo donde dice Breakout Rooms.
Breakout Rooms. Es que a mí no me sale, es lo que no veo.
En la partecita donde dice compartir pantalla, chatear, participantes.
Ujú.
Y ahí están unos cuadritos, una cuadrícula. Sección de grupos, dice. ¿Ya la viste? Si no, creo que los anfitriones te pueden pasar allá.
Ah, ok. Sí, porque no me sale participants, chat, share screen, record y es todo.
Sergio, ¿a qué sesión quieres unirte?
Pues es que no, como no veo cuáles hay ni nada, no sabría.
Son las de los 4 oradores. Tenemos la primera sesión, que era contribuciones a ZZB estrella. Tenemos la sesión de Stefan Nellen, que nos habló de materia oscura y acciones. Tenemos la sección de Víctor Muñoz Vitelli, que nos mencionó algo sobre cuerdas cósmicas. Y Edgar López, nuestra última plática sobre transiciones de fase en Qcd.
Bueno, es que más que nada quería saber cómo se hacía eso, porque como yo soy uno de los que presenta pósters, no quería quedarme fuera de cuando tenga que entrar al que necesite. Pero si me dicen que ustedes me pueden mover directamente a aquel grupo, pues entonces yo creo que no hay problema. Quizás sea que está desactualizada mi aplicación de Zoom, porque la descargué ya hace tiempo.
Okay. Hay una opción, en el menú también hay una que dice More en el mío y también aparece ahí.
A ver, menú.
O tal vez tengas tiempo de actualizarla.
Sí, View Options, Request Remote Control, Zoom Ratio. Sí, no, la verdad no veo por ninguna. Yo creo casi seguro que sí va a hacer eso de que tenga que actualizar. Voy a actualizar a ver si me aparece.
No estoy seguro que sea buena idea ahorita 20 minutos de la sesión.
Bueno,
mejor te mandamos
sí,
ahí.
sí es cierto, tiene razón. Mejor. Si ustedes me pueden mover, pues mejor.
Sí, yo creo que sí.
Sí, bueno, voy a comer aquí de carrerita. Muchas gracias.
José, ¿tú sabes algo de Mario Iván?
No, ¿te contactó?
No, por eso te pregunto si no te tiene algún problema o algo.
Bueno, le puedo mandar ahorita un mensaje a ver cómo está.
Vale, gracias.
Perdón, ya estamos en la sesión de pósters. Entonces, habría que, a ver si Jesús nos puede ayudar.
Sí, doctor, ya les mandé el comunicado de que pasen a la sala principal para cerrarlos.
Ah, ok, se van a regresar todos y luego los vas a mandar otra vez. Ok.
Sí. Listo, doctor, ya estoy creando las salas.
Gracias, Jesús. Entonces, para que todos estén informados, ahorita van a abrir las salas de los pósters y estarán disponibles en principio, pueden estar ya hasta el tiempo que quieran. Hay un tiempo aquí 2 horas, pero me imagino será más corto. Y bueno, los que no hayan visto todavía los videos, ahí hay un link en esta sesión que pueden utilizar para ver los videos, que están muy buenos. Yo los estuve viendo ayer, están muy interesantes y le han puesto mucho entusiasmo ahí en las presentaciones. También creo que va a estar el jurado de los pósters, va a estar pasando por hacer preguntas ahí. Va a haber, creo, al menos un ganador, que lo vamos a anunciar el último día.
Duda, ahora hace un minuto que he visto que tenía un símbolo de Breakout Rooms y era el 1, pero ahora salido y no veo más este símbolo, cambiaron algo ahí.
¿Wufang? No entendemos, está muy cortado.
Sí, ok. Hace un minuto que tenía todavía esta opción de entrar en Breakout Room, pero ahora no lo veo más, no sé qué, cambiaron algo que...
Sí, es que los salones se cierran automáticamente una vez ya que va a iniciar la sesión. Por eso sale el aviso para, pues, con un minuto de anticipación para alcanzar a despedirnos. Aunque sí, pues sí, creo que sí es poco tiempo y no todos alcanzamos a terminar, pero en caso de que sea necesario, si desean que creemos un canal, lo podemos abrir también para que haya otras charlas.
Yo creo que el bufón se refiere a que todavía no están listas las salas. Yo creo que apenas las van a abrir.
Sí, sí, ya, ok, entonces no es problema de mí. Ya, sí, sí, muy bien, gracias, sí.
Listo, doctor, ya están creadas las salas.
Ok, a ver. Sí, ya las veo todas.
Disculpe, ¿me puede pedir un favor? Si alguien me podría ingresar a mi sala del Breakout Room.
Sí, yo te ingreso. ¿Sí puedes alzar la mano para ver quién es?
Creo que es José Antonio, ¿no?
José Antonio, ok, perfecto.
Sí, José Antonio, ahí.
Antonio. Ok, permíteme.
Mi nombre es un poco mal escrito, pero no importa.
No, esta no era.
Disculpe, yo también voy a necesitar que me muevan a mi sala.
Sí, si puedes alzar la mano igual, por favor.
Ah, sí, mire. Ahí está.
Ok, vale, perfecto, espérame. Listo, doctor. ¿Alguien más tiene problemas para unirse a las salas?
Creo que ya están bien, porque veo que hay 13 salas activas y creo que en en el playlist de YouTube eran 13 pósters, creo.
Está bien, doctor.
Yusef.
Yes, hello.
Sí, ¿no deberías estar en una sala?
Sí, pero no sé cómo entrar.
A ver si Jesús te puede mandar para allá.
Es Yusef, ¿verdad?
Sí, por favor, sí. Sí.
¿A cuál vas a...? Ah, Premier, perdón.
El póster.
Listo, ya está.
Okay. Ahí está.
Ahí está, gracias.
Sí. ¿Alguien más tiene problemas para entrar a las salas?
A ver. Tal vez Ricardo no tiene una sala.
Ricardo. Ricardo. Ah, sí, lo paso. Listo, ya está en su sala, doctor.
Gracias. Jesús, ¿sabes qué pasa si me paso a una sala ahorita? Cuando estoy compartiendo, ¿se pierde?
Sí, doctor, se va a perder si pasa a la sala. Si quiere, páseme. Ah, no, lo está compartiendo desde la página, ¿verdad?
Sí, si quieres compartirla tú, estaré bien.
Sí, doctor, sí. Yo ahorita la comparto.
Sí, gracias.
Listo, ya voy a compartir.
Ok, muy bien.
Sí, doctor.
Gracias.
buscar las esferas del dragón. Vamos a buscar las esferas del dragón. Y